Right, Assalamualaikum and greeting to all. Okay, so today we will continue our second last chapter, which is chapter 24. Okay, so we stopped the previous lecture at slide 42. Okay, so it's about the helium formation. And now we continue with the deuterium and the density of the cosmos. Okay, so during the nuclear epoch, although most deuterium was quickly fused into helium as soon as it formed, so a small amount was left over when the primordial nuclear reaction ceased. So this observation from UV spectra indicate a present-day abundance of about 1 deuterium nuclei for every 50,000 protons. And however, unlike the helium, the deuterium is not produced to any significant degree in the stars, but instead will get destroyed. Okay, so for today, it must be the primordial that makes it sensitive and independent method of probing the present-day density of matter in the universe. Okay, so according to the theory of this, denser the universe is today, the more particles will at early times to react with this deuterium as it forms. So less deuterium will be left over when the nucleosynthesis ended. Okay, as we can see here, okay, the graph that shows still have the theoretical prediction here, okay, and the vertical line is the range of density consistent with the observation, and this horizontal line is represent the range of the observed deuterium abundance. So what is the deuterium abundance? Okay, so it's a part of the theoretical results that implies a present-day density at that value only a few percent of the critical density. So we have this, what we call that, nucleosynthesis process. Here depends only on the presence of the protons and neutrons. Okay, and normal matter, since the density of the normal matter is only 5% of the critical value, so we conclude most of the matter in the universe are dark, and not composed of proton and neutrons. So since normal matter and dark matter interact differently with the background radiation field, studies of the CMB allow us to distinguish between them. So CMB we have we have talked about that in the previous lecture. You can check it out. Okay, so the formation of the nuclear and atoms. For the first atoms is the atomic epoch, which consists of the electron, proton, helium, nuclei, dark matter. Okay, and the temperature was still too hot for hydrogen atom to exist. Okay, so this is the history of how the first atom be explained. Okay, so this period is known as the decoupling epoch, when this MB part accompany with normal matter. Then this period is called the recombination. Okay, so there was the free electrons there, and the universe was said to be opaque. It means the matter and the radiation were strongly coupled to one another, and photons can't travel far and were constantly scattered by the electrons. Okay, so the electron combine with the nuclei to form the hydrogen and helium. Okay, So the radiation of the other wavelength could travel virtually forever without being absorbed and making the universe nearly transparent. Okay, so this is the CMB photons that detected that travel through the universe. Okay. And the atomic epoch created a photosphere in the universe and completely surrounding the Earth at a distance of this, when photons last interacted before they decouple. Okay, you can see here the nuclei and the free electron surrounding the this photosphere layer. So this photosphere is created by the atomic epoch. Okay. So in the late 1970s, the standard Big Bang model had two nagging problems, which is the horizon problem and also the flatness problem. So the horizon problem concerns the remarkably isotropy of the CMB in all directions. And when we observe the CMB at two opposite, like here, A and B, opposite direction of the sky, so the isotropy suggests that they must have similar density and temperature. So the problem is there is no good reason that this region should be similar to each other. So this is the example of that issue. Okay. Okay, and how about the flatness problem? Consists the fact that this very close to unity. The total density of the universe is near the critical value with a geometry remarkably close to being flat. So the problem is here, okay, no particular reason that the universe should be so flat in the past, okay, no particular reason. So until the Big Bang here, also we can see the strip is different in color here, which represent the condition in the closed, critical, open, and accelerating. So if the universe is close to the critical, okay, critical, the purple one here, the critical density, it must have been extremely close to critical density in the past. So for example, since this equals to 0.3 today, then the departure from critical density at time of nucleosynthesis would have been only 1 part in 10 power of 15. Okay, this is about the dark energy acceleration due to dark energy and the observation that known as the problem. Okay, using the physical process. Yeah, and then we go to the cosmic inflation. During the early epoch, the theories that describe the unification of fundamental force rely on the existence of the scalar field. So the interaction is determine those particular properties. And we have these cosmic forces, one of the properties. Okay, and also the random quantum fluctuation. Okay, so some region of the universe will have even elevated state for some period of time that allow the empty space acquired in vacuum energy. Okay, so the temporary appearance of vacuum energy while remaining constant density could cause a region to expand at enormously accelerated rate. Okay, this is the inflation, so-called inflation. So this is the inflation epoch. Okay, in the GUT epoch, then you have okay, this one is the time since the Big Bang. So if we go through the time, then the last period here is the Quark epoch, and the first period here is the Planck epoch. So the leading models for the energy, we have this cosmological constant and the quintessence. Okay. And we also have the quantum fluctuation, the basic idea. So it's lead to the other speculation, okay, such as these three points here about the statistical equation and also the multiverse. Okay, so inflation will only be solved by the horizon problem, solve the horizon problem by taking the regions in the universe that were already in communication and drag them far apart and keeping their original physical properties. So the stretched region is more or less homogeneous, okay, and any initial differences between the parts have been smoothed out. Okay, so we have this one of the largest cluster, okay, is the diameter larger than the largest super cluster. Okay, so this is the illustration for the inflation process. We have before here, after, and today. So we can see the different when it run away with the time, then it's become bigger and bigger, and also the diameter also very depicts the very significant, okay, in their diameter. Okay, so we have this term of negative 26 and then negative 23, and then become bigger to mega 10 power of 4. Okay, so however, this visible portion of the universe has grown, okay, and still in microscopic in size. Okay, and our cosmic field of view is simply re-expanding into region of the universe that was within our horizon long ago. Okay, so this is the implication with the flatness problem here. Okay, so this is just quite interesting example for this issue when this issue is becoming very popular at that time. So they come up with this example. Okay, when you have this apa ni, locate and some animal, tak kisahlah animal apa kat situ kan. So it's walking down around the circumference of the circle. So from the radius of 10 cm and then 1 kilometer and then become far apart, 10 of 48 meter. So how this have been worked to show the flatness problem here. Okay, so since the universe is geometrically flat, so we conclude not only is most matter dark, but most of the cosmic density isn't made up of matter at all. Okay. So despite this theory information, we still resist by many scenes in its prediction. Okay, and we also have the supernova observation in 1990s. Okay, and then the go over into the vacuum energy about the to support the theory, and also the large scale geometry and the structure of the universe. So these observations are important to explain the galaxy formation. Okay, this is the formation of the structure. Okay, if you notice, it will not go far with the from the term quantum fluctuation, density fluctuations. Okay, so you maybe you can take into account where you have to maybe memorize this term. Okay, if this subtopic include in your final exam. Okay, you can check is it including in the final exam or not. I have stated there in the e-learning. Okay, so the growth of the inhomogeneities. Okay, so in history, so in 1980s they realized the galaxy could not form from the contraction of these inhomogeneities involving only normal matter. So these 3 points is explain these inhomogeneities here. Yeah, we have 4. So about dark matter, a normal matter cannot account for the large-scale structure we see today, but dark matter provide a natural explanation. Okay, so a dark matter started coming as soon as matter began to dominate the universe, which determined the overall mass distribution in the universe. So at later times, the normal matter was drawn by gravity into the regions of highest density and eventually forming galaxy and also galaxy cluster. So this is the luminous matter that strongly concentrate near the density peak. So it's okay, we have normal matter and dark matter, which dominant here. So the dark matter can be classified as either hot or cold depending on the temperature at the time when the galaxy began to form. Okay, so this both temperature will predict quite different kind of structure in the present day universe. Okay, so for hot dark matter, it consists of the lightweight particles where neutrinos are its leading candidates. Okay, so this model is based on the hot dark matter that are unable to explain the observed structure of the universe. Okay, this one is for cold dark matter. On the other hand, it consists of very massive particles formed during the GUT epoch or even before. Okay, and we have this computer simulation with 30% of cold and 70% that energy is to easily produce small scale structure and predict large scale structure in the observation. So yellow dots are star forming region. Okay? If you can see in this figure, there are yellow dots here. Okay, and then the filamentary structure, okay, and the generic features of the cold dark matter cosmological simulation. And yeah, okay, we go into replace in the radiation background. Okay, I will see this first. It's until the okay until 83. Okay, if we can see, maybe I can just summarize this all. Okay, for the dark matter. Okay, we stop here. Previous one. Okay, so this one is the ripples in the radiation background. So I think this also have been included in your previous lecture, I think, for the COBE. Okay, so this COBE is okay. So these ripples were too small to be measured accurately until this COBE announced its detection after almost 2 years of careful observation. Okay, so previously maybe they start with the manual detection for these ripples. Then when COBE is established, then they just use the automated punya ni lah way. So the temperature variation are only this temperature from place to place in the sky, and subtract the variation due to Earth's motion and radio emission of the Milky Way. Okay, so this is the resolution of the COBE. How consistent it is. So these two guys yang lead the investigation using this program. Later with NASA observed the CME with this resolution. Okay. And after that, they can get this kind of figure and result. Very quite a good results compared to before. So the map show temperature fluctuation. Okay, its angular power spectrum show characteristic of the angular scale of 1 degree, and the temperature fluctuation by multiple moment is measured by repeatedly splitting the map into half and measuring it. Okay, so this peak is determine the curvature of the universe. So it's excellent agreement with the universe. Okay, with this 30% of matter and 70% dark energy. So before decoupling, the dark matter is in overdense cloud with will have normal matter and radiation. Okay, so it's strongly coupled radiation push on the normal matter that cause the expansion rapidly outward in the shell. Okay, if you can see, so it outward in the shell. So, however, the gravity will weak, and the dark matter will try to prevent the shell from escape. Okay, so this interaction will cause the space to oscillate, sending out cosmic sound wave. Is known as the BAO, Baryon acoustic oscillation. Okay, we have been talking about this decoupling epoch before. And okay, the result in every dark matter region that form a galaxy, okay, is to be associated with the secondary shell of the galaxy. And then is a matter oscillation. Okay, so this term imprinted on the galaxy distribution in the universe. So all ripples that grow with the expansion will have a radius of this. Okay, and they will become the standard rulers, giving precise scale of the universe at different time in the past. So this one is a BAO just now. Okay, the probe is a probe of the expansion independent of the supernova studies. Okay, very quite interesting. So this SDSS, okay, I think you familiar with this term. It's a survey, it's kind of survey that has detected the BAO in 2005 that through the statistical measured separation of luminous red galaxies, LRG. Okay, so this is kind of the information of the cosmological parameters here. Okay, we have 6 cosmological parameters. The scalar spectral index that describe how the density fluctuation vary with the scale. And the curvature, fluctuation, amplitude describe how much different from flat the universe is. And we also have the reionization optical depth that refer to how much the CMB radiation has been absorbed or scattered between the reionization. Okay, so this cosmological parameters is successfully measured, okay, to unprecedented accuracy. So we'll have to explore the nature of dark matter and dark energy. Okay, yeah, so that's all for chapter 24. Okay, so we will continue our last chapter in the class. Okay, right. So see you all. Thank you.